Welcome to our video on merge sort. Merge sort is the fastest kind of sort that we are going to learn about. Now, the idea behind merge sort is you're going to take your array, divide it in half, then you'll sort each side of it, so you'll sort each half, and then you'll merge those two sorted halves back together to create one fully sorted array. So that's how it gets its name, merge sort, is when you take the two halves that have been sorted and merge them together. So I'm going to demonstrate this with cards. So we have 8 numbers in our array, and we're going to start by dividing it in half. So we're just going to take the left side and the right side, and we'll sort each side and then merge them. Now, how we sort each side is really important. We could do insertion sort or selection sort, but we know that those are slow, and we're going for fast with merge sort. So what we're going to do is we're actually going to sort each side using merge sort. So that means we're going to take the left-hand side and we're going to divide it in half. So we're going to split this into 2 halves. Then we're going to take each left and right. So this is our left, this is our right. And since there's only 2 numbers, we're just going to go ahead and sort those because that's just one comparison and maybe a swap. So on this left side, we're going to compare 50 to 49. We know 49 comes first, so we're going to swap these 2 numbers. Then we're going to take the right side and we're going to compare those. 28 to 39, they're already in the correct order, so we just leave them there. So now we have 2 sides of an array. Each has been sorted, and we need to merge them back together. So to do that, we start at the beginning of each side, and we compare these numbers. So we compare 49 to 28. 28 comes first, so we're going to put it at the first spot in our merged array. Then we're going to compare 49 to 39. 39 comes first, so we put it in the next spot. And then we just move in 49 and 50. There's nothing to compare them to. So now we have the left side of our big array completely sorted. And now we're going to move to the right side and apply merge sort. So for that, we're going to again divide it left and right. And then when we only have 2 numbers here, we just compare them. So compare 12 to 32. We need to swap them. Compare 45 to 20, we need to swap those. And now we're ready to do our merge. So we compare 12 to 20, so we're taking the first number from each side, comparing them. 12 comes first. Then we're still comparing 20, but now we're comparing it to 32. 20 comes first. Then we compare 32 to 45. And now we have our left side sorted, our right side sorted, and we're going to merge them back together to make one completely sorted array. So we're going to follow the same merge algorithm. So we take our first number from each side, 28 and 12. 12 comes first. Then 28 to 20, 20 comes first. 28 and 32. 28 comes first, 32 and 39, 39 and 45, comparing 49 to 45, and then when we're out of numbers on one side, we just take all of our remaining numbers and move them up here, and now we've ended up with a completely sorted array. Now you might have noticed that we are applying the same idea of dividing, sorting, and merging to smaller and smaller sets of numbers. This is a recursive algorithm. We apply it over and over, but the problem gets smaller and smaller until it becomes so simple that all we have to do is compare 2 numbers and possibly swap them. So usually this is implemented recursively, but it is possible to do it with loops as well. And the advantage of that is that it takes less memory. So anytime we're using recursion, it's going to take a lot of RAM in our computer. All right, now we're going to do another example of merge sort, but this time I've added a card so we have an odd number of numbers in our array, and I've added in duplicate. So we have 45 appearing twice, and we'll see what happens with this new version. So again, we're going to start by dividing our array in half, and since we don't have an even number, we're going to have to decide, is our left half going to have an odd number or our right half? And in this example, I'm going to make it be that our right half of our array is going to have the extra number in it. So I'm going to take these 4, make them be our left, and these 5 are going to be the right side. Now we're going to start by sorting our left side, and this is going to look really similar to our last example. So we divide it again, and then we compare 28 and 20. We need to swap those. 50 and 45 we're going to swap, and now we're ready to do our merge with these two halves. So 20 and 45, 20 comes first, 28 and 45, 28 comes first, and then these two fill in. Now we're going to sort the right hand side, and here we again have an odd number of cards when we do our divide. So I'm going to keep the odd number in the right hand side. Our left hand side just has 2, so we're ready to do our compare and maybe swap, but in this case they're already in the correct order. So now we're going to come over to our right hand side, and we have more than 2 cards, so we need to divide. I'm going to keep our extra card on the right hand side. So now our left has only 1 card. That's okay, it's already sorted, so we'll just leave it. We don't even have to do a comparison. Our right hand side has 2 cards, so we have to compare 12 to 32. They're in the correct order. So now we're going to do a merge, compare 45 to 12. 12 comes first, then compare 45 to 32, 32, and then 45. Now we need to merge the left and the right, so comparing 39 and 12, 12 comes first, 39 and 32, 39 and 45, and then 49 and 45. So now we have our left and our right sorted, and we're going to merge them together. So this is our final step. So we're going to compare 12 and 20. 12 comes first. Then we're going to compare 20 and 32. 28 and 32, 45 and 32, 45 and 39, and now we get to our duplicates, so 45 and 45. It doesn't matter which one we put first, we just have to make a decision. So we'll just go with putting the one from the left first, and then we compare 45 and 50. Oops, I messed that one up. There we go. So we've got 49 and then 50. All right, and now we have a completely sorted array. We had an odd number and a duplicate, but it worked out with merge sort. So at the beginning of this video, I said that merge sort is the fastest sorting algorithm that we're going to learn about. So now we're going to talk about why and how fast is it. So just like when we analyze the runtime of our other algorithms, we're going to say n is the length of our array that we're sorting. So when we start with n elements in our array, the first thing that we do is we divide it in half. Each half has half as many elements as the whole, so that gives us n over 2 elements in each half. Then we take each of those halves and we divide those in half, so we end up with 1/4 of the total elements in each of our sections. we continue this process of dividing in half and dividing in half over and over until we get down to sections that have only 1 or 2 elements in them. So we just keep going with this division process. Now this is really similar to binary search. Remember, in binary search, we divide our array in half and then check if we should be looking in the left or the right half and continue that process. So just like binary search, we figured out you can only do log-in divisions until you get down to just 1 element. The same thing is true when we're doing merge sort. We can only divide our array in half on the order of log-in times before we get down to 1 or 2 elements. Now when we get down to the bottom level down here, where we only have 1 or 2 elements in each section, we have to do a comparison and possibly swap each element. So that means in the bottom row, we're looking at each element once. So that's in comparisons. Then as we move back up, at each level, we're going to do a merge. So again, with the merge, that means we're comparing elements. We have to look at each element once, or maybe more than once in the context of multiple comparisons, but it doesn't really matter if we're looking at them once or twice or 3 times. When we're doing our big O notation or our runtime analysis, we don't care about constants. What we care about is our function in terms of n. So we're just going to say that at each level, we're doing on the order of n steps. So whether that's comparing or swapping or moving the elements. So now we have essentially a rectangle where we know the height, which is log n, and we know the width, which is n. So the width is our number of operations. So in each of these log n rows that we have in this tree, we're doing n operations. So we're just going to multiply our height by how many operations we do in each row, and that gives us n log n. And that is our runtime. So O of n log n is our worst case runtime. So you might remember from our other sorting algorithms that they had runtimes, in the worst case it was O of n squared. So that is not as good as n log n. If we look at these graphs, where our x-axis is n, our number of elements in our array, and our y-axis is our runtime, then n squared is going to look like a parabola. So as n gets big, we start getting really big runtimes. But this one, n log n, doesn't go up quite so fast. So it's going to look a little bit more like this. So it's faster because the runtime for any given n is going to be less than n squared. So merge sort is faster in the worst case than selection sort and insertion sort.